Next up, we have Max Ghenis. His talk today is on fusing economic survey datasets with the Synthimpute Python package. Max is founder and president of the UBI Center. It's a think tank that researches universal basic income policies. Previously, Max worked at Google as a data scientist. He earned his BA in operations research from UC Berkeley and an MS in data economics and development policy from MIT. Max, we're pleased to have you join us today, and I will make you co-host and please start your presentation.
Thanks so much for the intro, and great to be here at PyData. It's my second time here, but last year was a bit different. It was so it's good to actually have a live audience now. Yeah, as Jennifer mentioned, I am founder and president of the UBI Center. We're a think tank that researches universal basic income policies. And I'm actually also, we started a new, kind of spun off a new tech nonprofit called PolicyEngine. And that's really what I'm on, or what I'm here on behalf of today. So I will share my screen. Yeah, so what we do at PolicyEngine, our mission is to make everyone a policymaker. And we do that by producing a single unified product that lets anyone reform the tax and benefit system and see the impact both on society and their own household. To do this, we have to apply pretty complicated economic microsimulation modeling, and Synthimpute is a Python package that we've developed to make that more robust. So what I thought I'd do is give a little bit of a more background on PolicyEngine and a quick demo of our product, and demonstrate why economic policy analysis relies on data fusion, talk about some of the existing approaches to that and some comparisons of that, and also then, of course, how Synthimpute works itself and what's coming next. So some of what motivates us here is that taxes and benefits are just an enormous part of the economy. So about a third of GDP is collected as taxes among developed countries today. And that's up from about a quarter back in 1960. And a third of that third is spent on cash benefits. So this could be pensions, child benefits, welfare programs. And both of these numbers are moving upward. And there's just not really great analysis tools for understanding how those programs work. So even if you're in government or at a top think tank or advisor to a policymaker, you pretty much have to rely on these kinds of programs. So in the EU and the UK, there's kind of these semi-closed access Windows applications and very difficult to use, not intuitive. A lot of think tanks have their own closed applications. So it's really just behind the scenes to power their own reports and their closed source. In the US, if you want to figure out just, are you eligible for benefit programs like food stamps? Maybe your state has an estimator that'll tell you if you're eligible or not, but in many cases, you don't even get that. And if it's just eligible, you don't know what other benefits are you eligible for, or how much do you actually get. I've been pretty involved in some tax microsimulation tools. So there's a tool called TaxBrain, which is built by the Policy Simulation Library. And that's open source, and I think does a really good job, but it's really, it doesn't cover the benefit side. So in most cases, if there's a policy change that's being discussed, there's just no tooling at all to understand that. So my co-founder, Nikhil Woodruff, and I, we come at this from both a tech and data science and policy analysis background. So we both have contributed to open source models in the US and the UK. And we kind of met through working at the UBI Center, which is a think tank that I founded. And then as we started building this, essentially a front end for microsimulation technology, we realized it actually had more potential than just for our think tank by itself. So we're making it available to everyone, which it was before, but it's kind of in a different vein now. So our app, I'll go through in a second. It's a mobile-friendly web app that lets anyone design benefit or tax reforms. We also have an API, so folks who are interested in developing tools that might make use of both what people are eligible for in terms of benefits, what's their current tax liability, or how those kinds of metrics will change under policy reforms, they can use our API as well. And 100% of our work is open source. We actually developed the first open source microsimulation model in the UK, and we're the only tool that that provides this kind of front end for the tax and benefit side, completely open source. So we're all on GitHub. All right, with that, I'll jump to PolicyEngine UK. So we're live in the UK. We're currently building the US product. And here is kind of how PolicyEngine looks today. We hope to make it a little bit simpler in the future, but you go onto the site and you see a whole bunch of policy parameters that you can change. So we've got our tax system here. National insurance is kind of like payroll taxes for those in the US. And then a whole bunch of benefit programs. So universal credit is actually the biggest one, or mean tested program. State pension is also very, very large. And we also have some sort of user contributed sections, which we'll get into in a bit. So actually just Wednesday in the UK, there was a reform to the universal credit system, which was announced. So we can start with this and actually see a real world example here. So we've got a whole bunch of stuff. We can actually just repeal the whole program if we want to, or we can change the amounts that people get. We can also abolish different elements of it. But the thing that actually changed in the reform was this work allowance. So this is the amount that you can earn before you start losing your benefit. So this was raised by 500 pounds per year, which is 42 per month. So that's going to be 557 here. And plus 42 is going to be 335. The phase out rate was also reduced from 63% to 55%. So now we've got our policy. We can sort of see the plan up here, and now we can see the impact on the UK. All right, so we see that this reform would cost 2.7 billion. It would reduce poverty by 2%, and 12% of people would benefit. This is a pure additional spending program, so nobody comes out behind. And we can also see the poverty impact by age. So child poverty falls 4.3%. You can see that actually the third decile benefits the most on a relative basis. And also in terms of the share of people who come out ahead. So those in the third decile, about 1 in 4 of those come out ahead, compared to just 1 in 20, 125 in the bottom decile. And then the last thing is you can also describe your household. So let's say we're a married couple with a couple kids. You can actually change your employment income. Let's go to around 24K, see what happens there. And we can see, okay, this reform is going to pretty significantly affect the household finances for this person, this household, about 6% increase. And we can also see if they earned more or less, they might be trying to decide how should I get a raise, or what happens if I get a raise, or what happens if I work more or less. So we can zoom in on the area where the reform changes from the baseline, and we see from roughly, 6,000 employment income to about 35,000 employment income, they are going to come out ahead. And this all is customized based on the parameters that they entered. And finally, we have the marginal tax rate. So because the benefit program currently phases at 63%, that's a marginal tax rate that is added on top of the actual tax rate. So currently people pay about 75% marginal tax rates if they're sort of in the highest area. And this reform would kind of smoothen that out. So it would only rise to about 69% because the phase out rate falls. So that's basically the motivation for what we're doing here. I think I'll talk now about what goes into models like these with microsimulation and data fusion. So the general idea behind the kind of product that we work on, PolicyEngine and similar products, is if you were trying to figure out what is the impact on the poverty rate or the budget or the share of people who come out ahead or behind, You apply a technique called microsimulation, and this involves getting a government survey that's representative of the society, and each of these, usually there's tens of thousands of rows or so. You're going to have some information about that household, such as earnings, numbers of kids, marital status, maybe dividends, capital gains, other kinds of income. And you then have a program that runs through that for every household in the survey. So here's a very simplified kind of view of how this looks. You've got 100K earnings. This household has 0 kids, so maybe they pay $30,000 in taxes, and their benefits, they've earned too much to get benefits, so their net income is going to be 70K. This household's pretty similar, but they have some kids, so they're going to get a little bit more in benefits, so 76K net income. And then this household is going to actually per child get more benefits. They might also get benefits because they're just a low income adult. So their net income is going to be 30K. So you kind of do this for every household in the survey. Usually the households have different weights, so they represent different number of people in the population. So you're going to take a weighted sum of all of these numbers like tax liabilities, benefits, and that's how you get the total impact on society. So that's pretty simple if it's all in one survey, all the data you need. But let's say you want to combine multiple surveys. So for example, let's say there's a wealth tax that's being discussed. Well, you don't have wealth in the main survey data set you've used to calculate tax and net income. But there's a separate survey that has both earnings and wealth. So in the US, this is pretty concretely, this might be on the left side, the current population survey, and on the right side might be the survey of consumer finances. And this doesn't have all the information that you need to calculate all the other taxes and benefits, but it does have this wealth variable. So the question is, how do you use this data to estimate wealth in this data set? And there are a number of approaches that you could use. I think the key insight that we've found in Synthimpute is you actually want to predict the conditional distribution. You don't want to just predict a single number for each one of those. And that's because when you're computing taxes and benefits, you have to know the full distribution of values that it could take, because there's a very progressive, in many societies, there's a progressive system. So there's going to be a big difference between saying 3 households have an average of 10 million in wealth each, compared if you say, okay, 3, each of them has 10 million compared to one has 30 million, one has 0 million. Well, if your first 10 million is exempt from the wealth tax, those are going to produce entirely different tax revenue numbers. So that's why here we're basically saying we want not just, this is what we might call the point estimate of wealth. We want actually the full distribution of wealth based on earnings and number of kids that come from this data set. And then we're maybe going to pick a random value from within that predicted distribution. All right, so what this general problem is quantile regression is kind of a general approach to figuring out the conditional distribution. And a couple examples of tools that can be used for this. So here's a very simple example, just you're trying to predict one variable from one other variable. Ordinary least squares linear regression is going to have parallel lines. So you basically take your regression coefficient and then you have a standard error around that. So you can use that to estimate quantiles depending on the other covariates. And these are always going to be parallel. If you want to get a little more complicated, you can use quantile regression, where the slopes can differ, but they're still always going to be straight lines. If you want to get more complicated still, you can use non-parametric methods like random forests, which didn't do very well. I think random forests need a few more variables to perform well. Or TensorFlow. So this is a deep learning kind of approach where you're going to essentially identify different kinks in the data, but still going to be straight lines otherwise. So what we did to figure out what approach we should use when we're doing this for PolicyEngine products is use a real world data set. So in this case, we have a survey of consumer finances. We're going to try to predict the quantiles of wealth. And like any other kind of machine learning system, you want to have some way to predict on new data and see how it performs there. So we did a pretty simple 20% holdout. We could probably get similar results from other kinds of approaches. And we tried to predict wealth quantiles based on 11 features. So these features were things like where the income, the age, family size, marital status, and different types of earnings as well. And we predicted a few different quantiles. So 7 different quantiles are what we're predicting. And we do that with a few different methods. So I didn't show it here, but one of the most common approaches for this problem is essentially matching. So if we go back to this table here, we might just say, okay, what's the most similar looking record in this table and that table? So we're going to say, okay, 100K, 0 kids. I guess the most similar is going to be this 120K. And you can do this statistically, of course, and automatically, but that's going to give you 900K, where 25K maybe just grab the 22K. So yeah, that's a very common approach. So we tried that. We tried OLS. We tried quantile regression and also TensorFlow and random forest. And we evaluated with quantile loss. So what is quantile loss? This is kind of the key part of quantile regression. Quantile loss actually looks very similar to something you may have seen before if you're predicting the median. So at the 50th percentile, it's really just mean absolute error divided by 2. So 50th percentile, if you're either ahead or behind, your error is positive or negative, it's fully symmetric. So this compares pretty similarly to mean squared error, which is a very common loss function for example, OLS. It gets a little more interesting if you're predicting percentiles that are not 50%. So for example, if you're trying to predict the 90th percentile, the point at which 90% of the observations would fall below that, you're actually going to penalize errors that are too low more than errors that are too high. And vice versa for low quantiles. You're going to predict penalize low errors less for low quantiles. So the idea is you have to have different quantile losses for every quantile you're assessing. All right, so what did we find? Well, turned out random forest actually did the best by quite a bit compared to the status quo of matching. And this kind of makes sense because matching doesn't actually predict a conditional distribution, it predicts a single value. So OLS did better than matching, quantile regression did better still. TensorFlow and random forest were pretty similar. It turns out random forest is actually a lot easier to use because you can have just one single model. If you're familiar with random forest, it has a bunch of different predicted values, which usually are just used to figure out what the average is. But you can just use that to have an empirical cumulative predicted distribution. So you don't have to do separate models as TensorFlow sort of does for every specific quantile. So yeah, random forest did really well. If you also decompose this by each quantile, random forest did better than all the others on almost all of the quantiles, except the very top ones. So TensorFlow did a bit better at predicting the top, but random forest was still pretty competitive in that area, and it did better at the other quantiles. I will say, I think we could definitely do better with TensorFlow if we put more research into tuning it. But as I said, random forest is just ends up a lot easier to use. All right, so this is what led to our decision to use Synthimpute. And Synthimpute really just has one core function that is used, RF impute. So this imputes data with random forest. What it does is it takes a few arguments, but these are the 3 most important ones. And these are very similar to what other prediction APIs look like. So you've got your training data set on the Y, you've got your training data set as xtrain and your training labels, and also your new variables for x. So what this does is it calculates a conditional distribution for every record in x new, and it's going to select a random quantile within that distribution. So this is going to ensure that you're going to get a proper overall distribution, both on the aggregate level and also for individual, similar kind of records. And we actually have an option as well where you can have replicates of the x new, and it's going to predict multiple times. So you get the full distribution there. We also do something that goes beyond the standard RF impute approach, where you enter also your target overall value that you want it to sum to. So what this does is instead of selecting a random quantile, it's going to select a semi-random quantile. And this basically means it's going to select from some variable value from the beta distribution rather than a uniform when it's predicting which quantile to select. And it then optimizes this to say what were we going to do in terms of the average quantile to hit that target. So one example is food stamps are known to be underreported in survey data. So let's say we know that food stamps have $80 billion that are spent on them every year, but the surveys only say it's 50 billion. Well, if you're trying to impute data from that underreported value to make sure that hits 80 billion, there's still, you could just multiply by 8 over 5. But there are real values that are in the survey data that are more common than others, and that represents a real systemic feature of the program. So instead, if you say, I'm not going to just select so that the average quantile is 0.5, which is what the uniform distribution does, I'm going to select so the average quantile is 0.6 or 0.7. That adjusting that number is going to get you closer to hitting that 80 billion. So that's what RF impute allows as well.
Max, we've had a question from Lewis. He asks, did you try TensorFlow probability to check the distribution of results? No.
We actually developed this before TensorFlow probability was introduced. So yeah, I'd love to try that, actually. Thanks for the suggestion.
Thanks.
All right, I think almost done here. Just want to share a bit about where we're headed. So one of the things I think I showed it here. Maybe if we go back to PolicyEngine, we have this live in the product in one place, and that's the land value tax. So you can actually select a different value for tax on the value of land, and that's going to show up in the UK impact and those pages. So we do that by taking our core household survey, which is, the survey that has land value, which is the wealth and asset survey. So we can estimate land value there. It also has some other variables that let us match it to the family resources survey, which is the core household data set we use in PolicyEngine UK. So we use Synthimpute to do that. We also use the feature that I described of setting a target. So we want to do this for a lot more surveys. For example, the household surveys usually don't have data on wealth, land, of course, carbon emissions, consumption. So we can grab from these asset surveys, and these are going to differ by country, but we can grab it for wealth. We can grab, we can basically calculate carbon emissions in the consumption survey. And then if we want to do a carbon tax simulation, we can do that in the household survey as well. Same with the consumption tax, like a VAT. We can also use administrative records to improve the income in the survey. So for example, the current population survey in the US, the income is actually top coded. So if you have tens of millions of dollars in income, it's only going to cap that at maybe 1 million. So we can use tax data to improve that estimation. All right, and where does this go ultimately in terms of the product experience? Well, PolicyEngine, we want to build an app that is one vision where we have a much more democratic, participatory approach to policymaking, where you open your app and you kind of see from policymakers like political parties or think tanks or individuals policy ideas that everyone has, and we're all having the same data-oriented, personalized conversation around how those policies affect both you as an individual as well as society. And you can click in to see all the details I went through before, click into profiles to see what kind of policies individuals have put forth, but all this sort of unified and enhanced by having more accurate, more robust data underlying it. So that's all I have. Happy to take any questions. And yeah, you can go to PolicyEngine.org if you'd like to try it out. We're at the PolicyEngine on Twitter, and my email is max@policyengine.org.
Great. Well, thank you so much for the presentation today, Max.
Thank you very much. It was great to be here.